Okay, Chemistry 1401. Today we're going to try to wrap up Chapter 5, which deals with ideal gases and gases. And before we get into what's called the kinetic theory of gases, I want to back up a slide and I want to tackle a problem that we didn't get to finish during the last lecture. And the problem is this, and maybe I'll back up here because I might need a couple of slides to finish this thing. It says when 1 mole of methane is heated with 4 moles of oxygen, you get the following reaction. So this is the combustion of methane, and it produces carbon dioxide and water. And what it's asking us is what are the mole fractions of oxygen, carbon dioxide, and water in the resulting mixture. And remember that I told you what mole fraction was last class, that mole fraction, so is of anything, is equal to the number of moles of that component divided by the total number of moles. And so what we're looking for is when we have this reaction of 1 mole of methane plus 4 moles of oxygen, how many moles of carbon dioxide and water do we end up with? And what are the total number of moles of everything left over, right? Because we're going to need N total, and we're going to need the number of moles of oxygen, carbon dioxide, and water in order to figure out the mole fractions of each one of them, right? Okay, well, let's start out by rewriting the equation, and I'll show you why we're going to do that in a second. So we're going to start out with our methane gas, and we're going to combine that with 2 moles of oxygen gas, and we're going to produce 1 mole of carbon dioxide gas plus 2 moles of water, so steam. Now, when I said 1 mole plus 2 moles plus produces 1 mole and 2 moles, that's from the balanced equation. But what are we actually starting out with? I'm going to call that our initial state. Okay, I for initial. And what we're initially starting out with is 1 mole of methane and 4 moles of oxygen. We started with 0 moles of carbon dioxide and 0 moles of water, right? We haven't even done the reaction yet. Okay, we haven't done it. But if we think about the change, okay, what changes during the reaction? Well, if I look at my balanced equation, I know that for every 1 mole of CH4, right? Look, if I have 1 mole of ammonia, I look at my balanced equation and I see that for every 1 mole of methane, I see that for every 1 mole of methane, I'm going to consume 2 moles of oxygen, right? That comes from my balanced equation. So that means if I'm starting out with 1 mole of methane, I'm only going to end up using 2 moles of oxygen. So I'm going to end up losing all of my methane, but I'm only going to lose 2 moles of oxygen. Give me a thumbs up if you follow me on that. All the methane's going to be gone, but I'm only using up 2 moles of the oxygen. And if you're wondering, hey, does that mean the methane's a limiting reactant? The answer would be yes, absolutely. But this isn't a limiting reactant problem, so to speak. I just want you to give me a thumbs up if you follow me on the concept of consuming 1 mole of methane, and we're only going to consume 2 moles of the oxygen. Okay, great. Now, if we consume 1 mole of methane, that means we're going to form 1 mole of CO2, and it means we're going to form 2 moles of water, right? So that means we're going to form 1 mole of carbon dioxide, and we're going to form 2 moles of water. Again, that comes from our balanced equation. So final. So we have our initial, we have our change, and final. What do I end up with in the end? I'm going to tally up these two. Right? 1 plus -1 means I'm going to end up with 0 moles of methane. I'm going to have 4 minus 2, which gives me 2 moles of oxygen left over. I'm going to have a total of 1 mole of CO2, and I'm going to have a total of 2 moles of H2O. So that means at the end, I'm only going to have a total of 5 moles of gas. N total is equal to the number of moles of oxygen plus the number of moles of CO2 plus the number of moles of H2O, which equals 2 plus 1 plus 2. That equals a total of 5 moles, like that. Okay, I'm going to copy all of this. Okay, I'm going to copy this, copy that. Okay, we're going to bring that with us over to the next slide. Okay, so copy, and then we're going to put that. Hopefully I'll have enough space. No, I'm not going to, am I? Anyhow, here we go. So now, if I want to figure out what the mole fraction of oxygen and carbon dioxide and water are, all I have to do is take the number of moles of oxygen or carbon dioxide and water and divide that by the total number of moles. So I'm going to delete some more of this. I'll delete all of this here, like that. Bear with me, people. I'm trying my best here. So in the end, final, we're going to have 0 moles of methane, 2 moles of oxygen, 1 mole of CO2, and 2 moles of water, or water vapor, I should say. And so now I'm going to erase all this. Okay, we know that our end total, maybe I should use the object eraser. There we go. So now we know our end total. Adding this up. There we go. Okay, and we covered this on the last slide. Our end total is equal to 5 moles. So that means that the mole fraction, okay, of oxygen is going to be equal to 2 moles divided by 5 moles. Okay, so 2 over 5 is equal to 0.4. The mole fraction of CO2 is going to be equal to 1 mole over 5 moles, and that equals 0.2. The mole fraction of steam or water vapor is going to be equal to 2 moles divided by 5 moles, and that equals to 0.4. And so now we've answered A. We figured out the mole fraction of our oxygen, carbon dioxide, and water. In fact, you should notice that if you tally 0.4, 0.2, and 0.4, what do you get? You get a whole. You get 1.0. Now let's try the second part. It says if the total pressure, okay, in the second part, this is B, if P total is equal to 1.26 atmospheres, okay, what's the partial pressure of oxygen, carbon dioxide, and steam? And we know that the partial pressure of A is going to be equal to the mole fraction of A times the total pressure. So if we want the pressure of oxygen, it's going to be equal to 0.4 times 1.26. That 0.4 is an exact number. So when we take 0.4, we multiply it by 0.26, or 1.26, we get 0.504, 0.504. Sorry, I can't read my own handwriting. Atmospheres, we get for our pressure of CO2 is equal to 0.2 times 1.26 atmospheres, which is equal to 0.252 atmospheres. Sorry if my handwriting is messy. And then the partial pressure of our water vapor is going to be 0.4 times 1.26 atmospheres. And that gives us, of course, 0.504 atmospheres. What do you notice again? If you tally up all those partial pressures, what should they equal? They should equal 1.26 atmospheres. And so that is the solution. We've determined the mole fraction of the 3 remaining gases, oxygen, carbon dioxide, and steam. And using this formula, to mole fraction times total pressure, we've determined the partial pressure of each one of the 3 gases. And of course, in order for us to do that, we had to determine mole fraction first, right? So the 2 formulas that you ended up using here are mole fraction is equal to the number of moles divided by the total number of moles, and partial pressure is equal to mole fraction times total pressure, like that. All right, let's switch gears and talk about the kinetic theory of gases. Another way of describing what's summarized on this slide is these are the conditions for having an ideal gas. And in fact, at the very end of the lecture today, we're going to look at deviations from ideal gas law. Okay. The first point of the kinetic theory of gases says that gases are mostly empty space. The total volume of the molecules is small. I think that that's intuitive for most students. You know, if you take, something like, I don't know, an aerosol or a perfume that's in the gaseous phase, right? When you spray it, it vaporizes, the droplets vaporize into a gas. Well, you know that, you take something with a really small volume, okay, but it takes up a lot of space, right? If you just squirt, 1 squirt of an air freshener that vaporizes or something, that odor is going to fill the entire room, okay? And so if we take, molecules that produce an odor or something that we can detect in a big room, we know that if we condense all those gaseous particles down together, that we're going to end up with a very, very small volume of a liquid if we were to condense the gas to the liquid phase. And so that stands to reason that gases are actually mostly empty space, right? The total volume of the molecules is really small, and we're going to have huge spaces between each gas particle. The second point says that gas molecules are in constant random motion. And so we can assume that our gas particles, they're just moving around, right? And they might collide with the wall of a container, and then they're going to bounce like this, and then maybe they'll combine with another wall of the container, right? And they just keep going, right? In random, I'm trying my best here, they just keep going in constant random motion. You can think of I don't know if you guys are old enough to remember this, but on the DVD players, there used to be a screensaver where the DVD thing would be sliding around the screen, and the DVD icon was frictionless, as it were. It never slowed down. It just kept moving and bouncing all around the screen randomly. And so you can kind of think of the gas molecules as behaving in that way, in constant random motion. Okay, exactly. Joel says you always hoped it would hit the corner, right? There's an episode of The Office where they're all sitting around and waiting for it to hit the corner, right? And then they all cheer when it hits the corner. Anyhow, collisions of gas particles are elastic. Now, if you think about physics, classical physics, if you have ever played pool before and you hit a pool ball as hard as you can, is it going to rebound off of the side of the pool table? Well, the answer is yes, of course it will. But when it does, that because of the force of friction, the pool ball eventually is going to slow down, okay? But when we're talking about gas particles and this kinetic theory of gases and conditions for having an ideal gas, which of course, there's no such thing as an ideal gas, right? But we're talking about conditions where we can make a set of assumptions that a gas is going to behave ideally. We assume that the gas particle collisions are elastic. That means that they're not going to lose any of their velocity or any of their speed as they collide. And the answer is yes, Blake. They can collide with each other, but the collisions even between gas particles and the walls of the container are going to be completely elastic. Okay, so unlike classical physics where they're going to slow down over time, not in this case, right? We're not going to lose any of their speed. Okay, so elastic. Now, I would say that's also kind of related to polarity of a molecule. Remember we talked about polar and nonpolar molecules. If you think about the elasticity of these collisions, right? Blake asked. He said, "Well, what about if the molecules are interacting with each other?" Well, if you had two gas molecules or two atoms that are gases that are nonpolar, well, when they collide with each other, the collision is going to be more elastic than if you have, say, two gases that have a dipole moment, right, that are polar. Because if they collide, where you have a delta plus and a delta minus, there's definitely going to be some interaction there, okay? So again, this is an assumption we're making, that the collisions of the gas particles are completely elastic. We know that that can't always be the case, but again, it's an assumption we're going to make. Lastly, gas pressure is caused by collisions of molecules or atoms with the walls of the container. So again, this one is kind of related to bullet point 3, where since collisions are elastic, all of the energy is going to be used to push against the walls of the container, and that's what's going to cause pressure, right? These gas particles are pushing against the walls, and again, because of those elastic collisions, all of that energy is going to be used to cause pressure. So again, I consider these points relatively intuitive, in terms of our ideal gas. But if you think about the conditions where a gas would behave most ideally in terms of temperature and pressure, well, if we want the gases to be moving in constant random motion and to be colliding against the walls of the container and to be mostly empty space, that's going to be at a higher temperature, because we know as temperature decreases, the gas is going to condense and the particles are going to get closer together, right? We know that as temperature increases, the velocity or the speed at which the particles are moving is going to be faster. So it's going to be more of a constant random motion. So that means that when we have an ideal gas, the conditions are the preferred conditions for an ideal gas. We'll put ideal gas is going to be at high temperature. So at high T. Now, what about in terms of pressure? Is a gas going to be more ideal at high pressure or low pressure? The answer is low pressure, right? Because if we have a low pressure, then we're going to have that scenario where the gas is going to be mostly empty space. Once we start putting pressure on a gas, it's going to bring the particles closer and closer together. Okay, so an ideal gas, or any gas, I guess what I should say is any gas is going to behave more ideally at high temperature and low pressure. So if you're wondering, well, come on, will the ideal gas law, PV equals nRT, will that work at really low temperature? And will it work at really high pressure? Is it going to be applicable in those kind of situations? The answer is no. No, it's going to deviate from ideal gas behavior. And that's something that we're going to look at the very end of this, chapter. Okay, kind of something to think about as we move along here. Well, before I started recording this video, I was talking to the students informally, and I said, today I'm going to introduce you to a few equations that you're not going to be asked to necessarily work out any problems with these equations. And the first one that I'm going to show you is this equation here. I'm not going to ask you to use this equation, but I want you to understand the rationale behind this equation, okay? And I'm going to walk you through it, okay? And that is, if we apply the laws of physics to the kinetic theory of gases, we can show that pressure is expressed by this neat equation, okay? Never going to ask you to derive this equation. I'm not going to ask you to use this equation. Well, let's take a look at what pressure is proportional to, both directly and inversely proportional. So it says that P is equal to big N multiplied by M times U squared divided by 3V. What do these variables stand for? Well, N is the number of gas particles. Okay, and you can see from the equation that pressure is proportional, directly proportional to N. Does that make sense? The answer is yes. Think about it. We said just a few moments ago that pressure was caused by collisions of gas molecules against the wall of a container. So it stands to reason that, excuse me, the more collisions you have based off or due to the more particles you have, the greater number of particles, the higher the pressure is going to be. Okay, what about M? Okay. Little m is the mass of the gas particle. Well, let's think about that too. It's telling us from the equation that since m is in the numerator, that pressure is directly proportional to mass. Well, again, if pressure is a result of the collisions of particles against the wall of a container, look, if you have a car moving at 10 miles an hour, or a person walking at 10 miles an hour and they hit a brick wall, which one of them is going to have a greater force? The answer is the heavier object, right? A car is going to have exert a much greater force. What's pressure? Force per unit area. So it stands to reason that the greater the mass of the gas particle, the greater the force it's going to have against the walls of the container, and therefore the higher the pressure. Now the next one, U, is the root mean square speed, and we're going to talk about what root mean square speed is later on in more detail. But it's basically the speed of a gas particle, okay? It's obviously related to the speed of a gas particle. Let's think about that one too. You can see that pressure is directly proportional to the speed. Well, that makes sense too. If you have, let's say, a car going at 10 miles an hour colliding against the wall versus a car going at 100 miles an hour colliding against the wall, which one's going to have more force? The one that's moving faster. And so if we compare, two gas molecules that are identical, if we have one that's moving faster than another, it's going to exert a greater pressure. Okay? And lastly, V, you probably guessed what that is. It's volume. And we already talked about this when we discussed Boyle's law, that pressure is inversely proportional to volume. As the volume goes down, the pressure is going to go up. And as the volume goes up, the pressure is going to go down. Okay? So again, I'm not going to ask you to apply this equation to anything. But again, based on the laws of physics, okay, and this equation, I just want you to understand how pressure is related to the number of gas particles, the mass of the gas particle, and the speed of the particle, which, I don't like to make assumptions for my students, but I like to think that it's relatively intuitive. Now, I want to look at this equation in even more detail. So I'm going to rewrite it. So pressure is equal to n, number of gas particles, times mass, times root mean square speed, divided by 3 over the volume. Let's copy this. We're going to paste it into the next slide. Here's that equation that we were just looking at. If we look at isolating a couple of terms from this equation, if we look at number of particles per unit volume, what's that? Number of particles per volume. That's nothing more than concentration. So N over V is the concentration of gas particles in a container. It stands to reason that the greater the concentration, based off of everything we said, the greater the collision frequency, and thus the greater the pressure. Greater the pressure, right? We have simply more particles per unit volume. And then we're going to have more collisions, and we said that pressure was based off of collisions. What about this m times speed squared thing? Right, that's a measure of the energy of the collisions, and I'm sure that many of you have studied physics and have looked at the formula. Kinetic energy is equal to 1/2 times mv squared. But again, the rationale applies. If we think about mass and speed simultaneously in this portion of the equation, if we have a car colliding with a brick wall that's going at 100 miles per hour, so here we're taking something with a big mass and a big speed, okay, the energy transfer is going to be much greater than if a bicycle hit the same wall going at 5 miles an hour, right? Something with a smaller mass and a lower speed. Okay, so here again, you can see that pressure is directly related to mass times the root mean square speed. All right, that's enough on that. Now let's move on here. Average kinetic energy of translational motion. Now, you guys all know what kinetic energy is by now. That's something we talked about, I think, in the first week of class. Kinetic energy of an object is the energy which it possesses due to its motion. And we're talking about the motion of those gas particles. Remember the slide that I presented a few minutes ago? I said the gas particles are in constant random motion. The type of motion that gas particles possess is translational motion, which is the movement of an object that changes position. So from one position to another, right? As those gas particles are moving around, right? They're moving from one position to another, and that's opposed to rotational motion. But if we look at another formula, and again, this is a formula that I'm not going to ask you to use necessarily, but if we look at the average kinetic energy, and if you read our textbook, you'll notice that he or she, puts a line over the E like that for average kinetic energy. So the horizontal line means average kinetic energy is equal to 3/2 times RT over NA. So remember, NA, remember the last slide we looked at N, and here we're looking at NA. Those are not equal to each other, okay? On the previous slide, N was the number of gas particles. NA is Avogadro's number, okay? So the A stands for Avogadro's number, okay? So if we look at the average kinetic energy of gas particles, well, energy is going to be measured in joules. So we're going to need a different form of R, the gas constant. We're not going to use the 0.0821 liter atmospheres per mole Kelvin. I showed you a couple lectures ago how we get, or how we derive this form of the gas constant, which has joules as a unit. So we have joules in there. And then we have temperature in Kelvin in the numerator, and then we have Avogadro's number in the denominator. What is the take-home message from this slide? Let me tell you, let me summarize it for you very quickly. And whenever I say I'm going to do something quickly, I never do I? I always take a little bit of time to explain stuff for fun. Look at this. R is a constant, right? Maybe I should just cross it out. R is a constant. Avogadro's number is a constant. What did that tell you from this equation? Look at this, holy moly. Average kinetic energy is based off of temperature. I don't see anything in here about the identity of a gas molecule. Do you? I don't. All I see is that the average kinetic energy of a gas particle is going to be directly proportional, right? It's going to be directly proportional to temperature. There's nothing about the identity of a gas. It doesn't say polar gas, non-polar gas, doesn't say nitrogen, carbon dioxide, mass of gas. No, it's not even in there. Okay. So that's the take-home message from this equation. At a given temperature, okay, based off of what we just saw, we said that average kinetic energy is directly proportional to temperature. At a given temperature, all molecules of all gases, doesn't matter the identity. Okay, I don't care if it's nitrogen, ammonia gas, whatever. They all have the same average kinetic energy of translational motion. The average kinetic energy of a gas particle is directly proportional to Kelvin temperature. Okay, doesn't matter what the gas is. I know I've repeated that 5 times now, but that's important. All right, now I want to talk about the speed of these gases. All right, I want to talk about how fast these gases are moving and discuss the concept of root mean square speed. If you make a plot, okay, and you can see this beautiful graph here, if you make a plot of molecular speed, okay, versus the number of molecules, okay, at a given temperature, you see we end up with this kind of curve here that is not symmetrical. In fact, it rises pretty quickly and then it drops off kind of slowly like that. Okay. And you can also see that on the top, I have 3 speeds that we're interested in this class. Okay, there's 3 of them. You have the top of the curve, right? The highest point of that curve, that's the most probable speed. To the right of that, you have the mean speed. So that's the average of all the speeds tallied up. And then to the right of that, you have what's called the root mean square speed. And the root mean square speed, which you might not be able to tell from this, but it's is equal to, so it's the same thing as this u that I have here, okay? So the root mean squared is equal to the square root of 3 RT divided by the molar mass, right? This is molar mass in grams per mole. And this is temperature. So this is temp in Kelvin. Okay, so what do we get from this equation? 2 major points. They're summarized here for you. The root mean square speed is proportional to the square root of the Kelvin temperature. Does that make sense? It makes sense to me because that means that since temperature is in the numerator, as the temperature increases, the gas particles are going to be moving faster. Makes sense to me. Okay. You can also see that the root mean square speed is inversely proportional to molar mass. What does that tell us? It tells us that the heavier the gas, the slower it's going to move. The lighter the gas, the faster it's going to move. Okay, so root mean square speed. Now I have one problem, I think, in here that deals with root mean square speed, and this is one of those rare occasions where I'm not going to solve it with you. I actually just put the whole dang solution in here. A couple things I wanted to point out to you. If and this is a perfectly legitimate question. Okay, this is one of those equations where I could ask you to solve this. I'd have to double check the handout for your next exam, which is midterm 2, but I'm pretty sure that I give you this formula. I'm going to ask you to memorize this formula. Root mean square speed is equal to the square root of 3 RT over molar mass. If you were asked this question, calculate the root mean square speed, U, of nitrogen, of a nitrogen molecule at 25 degrees Celsius. In this case, you have to use a different R. And if you go back, and I'm not going to back up because it's quite a few slides ago, but if you back up quite a few slides ago, we looked at actually 3 values for the gas constant. Okay, we looked at 0.0821 liter atmospheres per mole Kelvin. Then, even today, we've looked at 8.31 joules per mole Kelvin. Well, keeping in mind that a joule, right, 1 joule is equal to 1 kilogram meter squared per second squared. From that, you can derive that the gas constant, which can also be written as 8.31 times 10 to the power of 3 grams meter squared over second squared. Okay, and that's the value of R that you're going to use in this equation. Okay, you're going to use 8.31 times 10 to the 3 grams times meter squared per second squared. So we have 3 times that gas constant, which is shown right here, Okay. Sorry, I'm leaving out my units. Per mole K. Sorry, my bad. I'm so hepped up on the joule that I forgot to include part of it. Again, my mistake. I feel like I don't make that many mistakes, but that's a pretty stupid one. There we go. So there's our whole damn gas constant, okay? And then we have our temperature divided by our molar mass. All right. Now we have to have our gas constant with grams instead of kilograms, okay? Which we have, 1 joule is 1 kilogram. Well, when we do that, look what happens. We have our grams canceling, we have our moles canceling, we have our temperature units cancel, and we're taking the square root of meters squared per second squared, which gives us meters per second. And I know that everybody that's hearing the sound of my voice, there's nobody that's hearing the sound of my voice that can't work this out. If I was to set this up for you and say, take the square root of all this, you'd be like, sure. 3 times 8,310 times 298 divided by 28.02, sure, press the square root button, and you end up with 515 meters per second. Now that's a pretty fast speed. Think of how far a yard is, okay? A yard is pretty close to the same length as a meter. Okay? It's a little less than a meter. So that means the gas particle is going 515 meters per second. We're like, yeah, that's fast. Now, if we calculate that in terms of miles per hour, we get that it's going what? 1,150, right? So this would be 1,150 mph. That's fast. You think about getting hit with something that you could see with the naked eye. If you were to get hit by something moving that fast, I mean, that's faster than a bullet. That's fast. That would hurt you a lot, okay? But luckily, the mass is small, right? The mass of a nitrogen molecule, N2 molecule, is really small. I'm just looking at my notes here while I'm lecturing, and I said, N2 is hitting your face at 515 meters per second. But the size of nitrogen is on the order of 10 to the -9 meters, or around, a nanometer. So we don't feel it, okay? So since it's such a tiny little bullet, you don't feel the force of the nitrogen molecule hitting. I don't know why I chose your face, but that's what I put in my notes. N2 is hitting your face. Anyhow, I have funny ways of thinking about things sometimes. Anyhow, where was I? Yeah, so that's an example of a problem where you would be asked to calculate root mean square speed. Give me a thumbs up if you think you could nail that. Calculate a root mean square speed. Like, just watch me. Just watch me do it. Okay, good. Thanks, Blake, Violet, everybody. Good. Okay, wonderful. All right. Well, we're getting close to the end of the chapter now, and there's a couple more concepts that I want to look at with you. First one is diffusion, and the next concept is effusion. Okay, so diffusion and effusion. See if you can get these things straight in your mind. And diffusion, gas diffusion, is the gradual mixing of molecules of one gas with the molecules of another by virtue of their kinetic properties. Oh boy, I might have to turn my camera on to demonstrate this one here, but look at this. Hey, this is the molecular path that I was trying to draw earlier, right? Remember, gas molecules are in constant random motion. And they're just, switching directions without even hitting the walls of a container. They're just in random motion. Okay, here's a scenario that really explains this concept well, I think. There is a law that tells us that the rate of diffusion, let me just write it down here, rate of diffusion is inversely proportional to the square root of molar mass. What does that tell us? It tells us that a lighter gas is going to move faster than a heavier gas, okay? So we'll put here lighter gas moves faster. And also a heavier gas is going to move slower. Now, if we use that law, that rate is proportional to the inverse of the square root of molar mass, we can derive this equation here, which is the rate of the diffusion of one gas over the rate of the diffusion of another gas. So we're comparing their rates is going to be equal to the inverse of their square root. So the square root of the molar mass of the second gas over the molar mass of the first gas. Now, I'm thinking of too many things here at once, but I really want to get to this picture with you. Okay, a picture is worth 1,000 words. Here's a scenario where you have a bottle of ammonia and a bottle of HCl gas. Okay, so these are both gases. This is ammonia gas, and this is HCl gas. Which one of those gases is lighter? Well, ammonia is lighter, right? It's like less than half the mass. And so what's going to happen if we open up these two bottles? Opening up a can of gases, right? You're going to have some ammonia gas, right, coming out the top here, and you're going to have some HCl gas coming out the top here. Now remember that when you combine ammonia and HCl, an acid plus a base, we end up with a salt in this case. So if we combine ammonia plus HCl, which is a gas, we end up with an ionic compound, ammonium chloride, and ammonium chloride is a solid. Okay, so you see all this white smoke here in the air? What that is that's ammonium chloride precipitating out of the air. So what's happening is you have the two bottles. Look, I'm going to have to turn my camera on for a second here. How do I do that? Stop presenting. Where am I? Here we go. Can you guys see me? Can everybody see me? I just want to be 100% sure before I start explaining. Okay, cool. All right. So, I don't know. This is the best demonstration I can come up with. Here's our ammonia gas, and here's our HCl gas. Look, when they combine, they're going to form an ionic compound, which is that white solid that's in the air. Okay? Look, if the ammonia is going to move faster than the HCl, right, it's going to come over here. And that's why the cloud that was formed was closer to the HCl side. Watch this demonstration. Look, the gases are both moving, but the pink one is moving faster. Okay? And that's why the cloud that's formed is closer to the bottle of the heavier gas. I'm sorry, but that's the best I can do. Does that make some sense to anybody? Give me a thumbs up if that makes some sense. Lighter gas is going to move faster, and therefore, yeah, you want me to tell you a way that I could ask that as a question on an exam? Okay? And I'll go back to my presentation here while, oops, how do I go back there? No. Sorry, you guys. There we go. Okay, an easy way to ask this question, and I've asked this question before on other exams, is this. Okay, so just listen to the sound of my voice because I don't have this question written down. But I said, okay, you open up a bottle of, I don't know, 4 gases, or you open up 4 different bottles with 4 different gases. Which one are you going to detect with your nose first? You know, assuming, yeah, just based off of gas diffusion laws. And I give you the molar masses of all the gases, assuming they're all at the same temperature. Okay, whichever one is the lightest gas, that's the one you're going to detect with your nose first because it's going to travel faster. Okay, so the ammonia is traveling fast and the HCl is traveling slow. And so the cloud is closer to HCl. All right, so that's gas diffusion. Next, we're going to look at effusion. In effusion, Graham's law of effusion. Effusion is just gas escaping under pressure through an aperture or through a small hole. So according to Graham's law of effusion, a gas under pressure escapes from one compartment to another compartment by passing through a small opening. You probably recognize this portion here from the last slide, but now we're comparing rate and time. So let me write that down maybe. Okay. So R is equal to rate and T is equal to time. And you can see that rate and time, rate is inversely proportional to time. Does that make sense? I think that makes sense, right? Because if you have a low rate, let me choose a different color here. If you have a low flow rate, I'm going to have a longer time, okay, longer time. And if you have a high rate, if your R is a big number, you're going to have a shorter time. You're going to have a smaller t. Okay, so it stands to reason that rate and time are inversely proportional to one another. So Graham's law of diffusion. All right, well, let's see. I do have a problem that involves Graham's law. This one here. You have a flammable gas. It's made up of only carbon and hydrogen, and it's found to effuse, so this is effusion, through a porous barrier in 1.50 minutes. Under the same conditions of temperature and pressure, it takes an equal volume of bromine vapor, 4.73 minutes to effuse through the same barrier. Calculate the molar mass of the unknown gas and suggest what this gas might be. Okay, so we're going to need the formula for diffusion, right? And we said that T2 over T1 is going to be equal to the square root of the molar mass of 2 over the molar mass of 1. All right, we're given some times. So let me move on to the next slide so that I can write everything down here. Okay, so here's the formula we're going to need. We're given our time for our hydrocarbon gas, which we'll just call CXHY, I don't know, like that. So we'll say the time for CXHY, which is our hydrocarbon gas, is equal to what? What was it? 1.50 minutes. And the time for our bromine gas, 4.73 minutes. We know the molar mass of Br2, just 79.9 times 2. So the molar mass of Br2 is 159.8 grams per mole. And what we're looking for is the molar mass of CXHY. Well, let's start plugging some numbers into our formulas here, or our formula is down here. And then we can take all this spinach here, and we can plug that into our formula. And we'll say that 1.50. So let me rewrite the formula. Son of a gun. Just worried. I'm always worried I'm going to run out of space. So yeah, so if I have my T of CXHY over the time for my Br2, it's going to be equal to the square root of molar mass of CXHY divided by the molar mass of Br2. All right, now let's start plugging in some numbers. So we have 1.50 divided by 4.78 is equal to the square root of, we'll just call it X over 159.8. I didn't do this problem yet, so let's see. So we have 1.50 over 4.78. We'll square all that, and then we'll multiply by 159.8, and that should be equal to our X. Let me just call it what it is. Our MCXHY. Here's my calculator. Is anybody like me? I always have 3 calculators on my desk. So let's see here. 1.50 divided by 4.78. We square that. So that's, oh, is it 4.73? 3. That. Okay, so 1.50 divided by 4.73. Square that. And we're going to multiply that by 159.8. And we get 16.8 1 grams per mole. Well, this is pretty obvious as to what the idea of the gas is, because if it's got carbon, carbon weighs 12.01 grams per mole, and hydrogen weighs 1.01 grams per mole. Well, if the molar mass of the gas is 16, it can only have 1 carbon, right? So it's got 1 carbon, and then how many hydrogens do we have for every carbon? Well, if we have a total mass of 16 and each hydrogen weighs 1, we must have 4. Son of a gun, it's flying around. So the gas must be methane. This is methane gas. All right. Give me a thumbs up and follow me on that one. I'm not sure if I understand your question, Lauren. If you're asking, are you asking about units? Like why I didn't include the units? Anyhow, I'm not sure if that's what you're asking, but the reason I left the units out here, right, is because the minutes over minutes, they cancel. So the minutes are gone, and I probably should have put grams per mole in here like that. So you're multiplying by 159.8 grams per mole, but the minutes are gone. All right, there we go. Or maybe it's because I put in 4.78. I don't know. I can only keep such good track of the chat while we're going on. Okay, distribution of molecular speeds. At a given temperature, gas particles will have a set of speeds. So we're going to have a range of speeds at a particular temperature, right? We looked at that curve earlier on. Right, you saw a curve a few slides ago, and we saw that on the x-axis we had molecular speed, and then we had what on the y-axis? We had the number of particles. So number of particles, particles, okay? And we had a distribution that looked like this, where it rose quickly and then it kind of tapered off like that. That's called a Maxwell-Boltzmann distribution, that curve, okay? And there a lot of work went into discovering and understanding the Maxwell-Boltzmann distribution. In fact, it's James Clerk Maxwell and Ludwig Boltzmann who together, came up with this equation, which you'll never have to use, but it describes, it describes that curve, that shape, okay? So again, at a given temperature, you see that we have this whole range of speeds, right? If the x-axis is speed, we have a whole range of speeds, right? Going from slow speeds to high speeds. Well, what do we need to understand from this curve from this equation is sort of 2 things. And I'll just kind of break it down for you really quickly because I'm never going to ask you to apply this equation. But the Maxwell distribution plot depends. So this is a Maxwell Boltz, distribution. Okay. It depends, this curve depends on a couple of things. It depends on temperature. Okay. And from down here, it also depends on the mass. So this is related to the mass of the particle. So 2 things, the temperature and the mass. Now I'm going to show you how those variables, temperature and mass, actually affect the curve in a second. So if we plot the fraction of molecules having a speed versus the molecular speed, okay, so if we make a plot, okay, of the fraction of molecules having a certain speed versus molecular speed, we get a curve that results that has a maximum in the number of molecules with a given speed, and we call that the most probable speed. Remember when I showed you the curve, it looked something like this, and wow, that's not a very good Maxwell-Boltzmann, is it? It looked something like this, and I told you that the top of the curve, that's the most probable speed. Okay, most probable speed. As the temperature increases, what you're going to see is that curve is going to shift. The maximum, right, this point is going to shift towards the right, towards a higher speed. So as temperature increases, you're going to get that curve moving over, but it's also going to flatten. And so the relative number of molecules or atoms at that speed is going to decrease. Let me show you, because a picture is worth 1,000 words. So we have number of molecules on the x-axis, and we have molecular speed on number of molecules on the y-axis, molecular speed on the x-axis. Now, remember this equation that we looked at, I don't know, a while ago. That root mean square speed is equal to 3 RT over molar mass, and we take the square root of all that. Okay, what does that tell us? It told us that root mean square speed was proportional to temperature. Right? It told us that U RMS is proportional to, it's actually the square root of temperature. But good enough. What does that mean? As the temperature goes up, the average, or the root mean square speed, which you remember lied to the right of the most probable speed, is going to increase. All three of these curves are for the same gas. They're all for nitrogen gas. And as the temperature increases, what happens to the curve? Right? The most probable speed and the root mean square speed shift to the right. The excess is higher molecular speed, but it also flattens out during the process. What else? We see that the root mean square speed is proportional to 1 over the square root of molar mass. What does that tell us? All three of these curves, which you see here, they look similar to these ones, don't they? But it's a completely different scenario, because what we changed in that first one was the temperature. Now the temperature is constant for all of these, but what are we changing? We're changing the molar mass of the gas. And since they're inversely proportional to the molar mass, that tells us that the lower or the lighter the gas, the lower the molar mass or the lighter the gas, what's going to happen to the root mean square speed? It's going to increase, right? It's going to get higher and higher and higher. All right. That makes sense based off that demonstration that I did earlier today. Remember when we were talking about the HCl gas and the ammonia gas? We said, well, the ammonia gas travels faster. Why? Because it's lighter. Okay, and so the average speed, or the root mean square speed, however you want to slice it, of a lighter gas like helium is going to move or be higher than that of nitrogen, which would be higher than that of chlorine. All right, so those are the kind of concepts that you want to understand from that equation. Now, this is really the end game of this chapter. We've got 2 slides left, okay, where we're going to discuss deviations from ideal gas behavior. Now, if you took 1 mole of an ideal gas and you put it in a container, you take that 1 mole of any ideal gas, you measure the pressure, the volume, you take the gas constant and the temperature. You measure PV and you divide it by RT. What should it equal? It should equal 1 mole, right? Because you put in 1 mole of an ideal gas. Now, what you can see from this zoomed in portion right here is that on the y-axis, we have that PV is equal to nRT, and they've highlighted, 1. This would be perfect ideal gas behavior. You can see that all of these gases that are plotted, methane, hydrogen, carbon dioxide, and helium, you can see that none of them follow that line exactly, and we're going to explain why that is. But first, I want to draw your attention to the zoomed in part, okay? You can see it's really small, okay? And you can also see that if they're just zooming in that little tiny part, I mean, down here, this isn't even a deviation of, 0.9, okay? So it's very small deviation. And you can also see that 1 atmosphere would be right around here. So when we're at 1 atmosphere, right, you can see that all gases, behave pretty close to ideally. None of them are going to be perfectly ideal. And in fact, there's an interesting table that's in our textbook that shows you the volume of 1 mole of all these gases at standard temperature and pressure. And it's never exactly 22.414 liters. They always deviate a little bit. But the idea behind what's zoomed in here, okay, the idea that I want you to understand is that when we're close to 1 atmosphere of pressure, that all of these gases are kind of right here, and they do behave pretty much ideally. What happens if we change the pressure? Right, you can see we're going from a pressure of 1 atmosphere, which would be very close to the y-axis down here on the x-axis, and we're going up to crazy pressure, what's going to happen? Well, let's think about this equation, PV over RT. If we start to increase that pressure, the first thing that happens is that you notice that in some cases, the curve dips below. You get n is equal to a number that's less than 1. Now, when would that happen? That would happen when the numerator gets smaller, right? Because R and T are constant, okay? So when does that happen? That happens when the pressure drops. And the reason why the pressure drops is based off of the effect of, nope, I'm highlighting the wrong spot. The effect of interparticle attractions predominates. So as you start to increase the pressure, you just start to increase it for these gases. What are the two here? Methane and carbon dioxide. So for these two cases, when that curve dips below the behavior of ideal gas, okay, the reason why is because when you start to squeeze those gases or put them under pressure, all of a sudden those particles of gases are going to start interacting with each other and they get attracted to each other, okay? Notice that it says here, attraction. They attract each other. What happens if they start attracting each other, right? If they're attracted to each other, their collisions aren't elastic anymore, are they? No, they're not. That means they're not going to hit the walls of the container with this greater pressure or greater force, resulting in a high pressure or as high a pressure, right? So as they get more and more attracted to each other, what's the net result? The net result is that there's going to be less pressure, and that's going to cause this P to be lower. This is going to cause the numerator to decrease, and it's going to give us an N less than 1.0 moles. Now, you can see that all of them get above that N is equal to 1 mole, right? They all get up there once you get into high pressure, really high pressure. And I bet you can get most students, I find this part more intuitive. Now, why would it be when you jack up the pressure like crazy on all of these gases? Doesn't even matter. All these gases, the same darn effect happens. Wow. All of a sudden, PV becomes bigger than RT, and you get a number greater than 1. Now, why would that happen? Because you know that even though in the ideal gas law, we assumed that the gas particles in an ideal gas, that they had a mass, but we assumed that they had negligible volume, didn't we? What was something I taught you at the beginning of this class? That matter is going to take up space, right? So we know that that's not true. We know that a gas is going to take up some space. So as you start increasing and increasing and increasing and increasing the pressure, all of a sudden the volume of the gases starts to count, doesn't it? Right? It's going to start to be important, and you're going to have to take that into account. Okay? And so what does that mean? That means the volume is going to be bigger than you would assume it would be based off of ideal gas law. And the numerator is going to increase, and therefore your N is going to be greater than 1. Okay? Now, if you're wondering, hey, can I correct for all this? Is there a way I can correct PV is equal to nRT for all of those, for the deviation from the ideal gas law, right? The ideal gas equation was PV is equal to nRT. Well, what were the two things that were affected? Right, the two things that were affected when we deviate from ideal gas behavior are pressure and volume. And in order for us to correct or to make the corrections for pressure and volume, we have to use the van der Waals equation, which is for a non-ideal gas. And here you can see that we have a correction factor for pressure, and we have a correction factor for volume. Now, if you look at our book, we definitely have some problems in the back of the book where you have to apply this. In fact, I've taught this several times where we've actually had to use the van der Waals equation. Of course, I would provide that for you, but I don't ask any questions about it on your next midterm or on the, because it's not covered on the ACS, okay? But what do you notice about the volume? One thing that I just want to point out to you is that if you look at the van der Waals constants, let me use a red pen. If you look at the van der Waals constants from this table, what do you notice about, B, the correction factor for volume? You see that generally speaking, generally speaking, and again, this is a general trend, that it increases as the gases get bigger, right? Because they're going to take up more and more volume. So as a molar mass increases, generally you're going to see that the corrected volume is going to get bigger and bigger, right? If you compare something like carbon tetrachloride, with, say, helium, right? Helium is a much lighter gas than carbon tetrachloride, and so you can see that its correction factor is less.